Sometimes it's not enough to have a single op-amp for a specific function. Uh, a good example is if you want to have a very high gain uh, that cannot be provided by a single op-amp, so you'll be forced to connect the output of one op-amp to the input of another op-amp in order to obtain a higher gain. Sometimes there are also desired functions that cannot be simply accomplished by a single op-amp that uh, would require a lot of op-amps um, to attain that function. So such connection of two or more op-amps are called cascaded op-amp circuits. So let's have an example of cascaded op-amps. So here we have three op-amps, two of which the outputs are fed to the inverting terminal of a third op-amp, which is obviously the final op-amp in the process. So these two op-amps is where the two input voltages come in, and the output is taken from the third op-amp on the rightmost. So the inputs to the two op-amps are V sub 1 equals 7 volts and V sub 2 3.1 volts. So the question is, what is the output V naught? Okay, so let's solve this on a per op-amp basis. So let's start with this op-amp. So this one is a voltage follower, meaning whatever is the input uh, should be the output. So this follower is the same configuration that we have shown earlier. So therefore, the output here must be 7 volts. Okay, so this one is 7 volts. This one is we have here 3.1 volts. Okay, so how about this one? What is the output of this? So let's uh, designate the output here as V01. So this is V01, and here let's designate the output as V02. Okay. So how do we get V02? Well, we can apply KCL here. This terminal is 0 volts. Since this is an ideal op-amp, so this is 0 volts. So the current here is 0, okay, as well as in this terminal, the current is 0. So let's say this is the direction of the branch current here, and also this is the direction here. So current entering equals current leaving. So current entering here is 3.1 minus 0 divided by 10, and that should be equals to 0 minus V02 or VO2 divided by 50 kilo ohms. So that gives us VO2 equals to 15.5 volts. This op-amp, this is 0 volts. There's no current here. Uh, there's no current here also. And this node should also be 0 volts. Okay, so the current here must be the sum of this current here and this current. Okay, we can compute this current as equals to uh, VO2 minus 0. So this is 0 divided by 30K, right? So that gives us 15.5 divided by 30K, or that would give us uh, 0.5167. So by the way, this is negative here. Okay, so therefore this should be negative. Also, for this current through the 20 kilo ohms, that current should be equals to V01 minus 0 divided by 20K. Okay, so this should be milliamps. So that would give us, so this should be 0.35 milliamps. Okay, since the current here is 0 and here this current will go directly there. So that means that if I let this as I sub f, for example, and say I let this I sub t, that means that um, I sub t must be equals to I sub f. But I sub t is equals to 0.35 plus this current, which is a negative, so 0.5167. And that is equals to I sub f, which is also 0 minus V naught divided by 60K, right? So therefore, I can compute for V naught, and uh, that should give me 10 volts positive. Okay, so this is the final answer. Here is a more detailed uh, view of the branch currents and the node voltages for this particular example. In our next example, we are to design an op-amp that subtracts two voltages, V sub 1 and V sub 2. So meaning that, let's say, this is my design. So this is my design here. I don't know this yet, and I have two inputs. So let's say this is V sub 1 and this is V sub 2. I want my output to be equals to V sub 1 minus V sub 2. Okay, so the question is what should be the design of this cascaded circuit? To do this, we could break down the function. Um, so we have here V sub 1, and we have here, for example, V sub 2. And what we can do first is we can invert the signal. So we use an inverting amplifier, so that this will produce a negative V sub 2. And then we will use a summing amplifier to sum up these two so that what will come out is V sub 1 plus the negative of V sub 2. Okay. Now for the inverter, so let me do this on another page. For the inverter, we can use the inverting amplifier that we have discussed a while ago. So the inverting amplifier would probably would look like this. So this is negative, plus, and this is uh, on ground. Um, this will be uh, our V sub 2. Okay, this will be R sub. Um let's call this R sub 2, and this is our feedback resistance. So we call this R sub F. So the output here would be um, equals to the negative of Rf over R sub 2 times V2. Okay. Now we let R2 equals Rf. So that means that the output will become negative Rf over Rf V2, or simply negative V2. Okay. Then, so we let this resistance here equals to Rf. Okay. Um, then here is our V1. Okay. So we need to sum up V1 and the negative of V sub 2. So therefore we use the summing amplifier. So for the summing, so this is the minus, it's the plus. The plus is connected to ground. Uh, so this is the inverting input. So this is V sub 1. Okay. So it will need a resistance. So let's say this is R sub 1. Okay. And the output of this first op amp also must have a resistance connected there. So let's call this R sub 3. Okay. And it will have a feedback. Let's call it also R sub F. Okay. So this is R sub F. Now the output of this, let's call this output V V naught prime. Okay, so the output of this would be negative times Rf over R1 times V1 plus Rf over R3 times the negative V2. Okay, so that is the output. Then we let R1 equals R3 equals Rf. So both R1 and R3 are equals to R sub F. So that means that this expression will become, so this is B prime, B0 prime, it will become negative Rf over Rf, V1 minus Rf over Rf, V2. Okay, and this will become V2 minus V1. Uh, so this is our V not prime, but this is not what we want. We want V sub 1 minus V sub 2. So again, we reroute the output of this to another inverting amplifier, so which has so this is minus, this is plus, this is ground, this is the feedback resistance. It's called this V naught. So this is RF, and also make this RF. So this circuit is actually the same as this one. So finally, we have V naught equals negative R sub F over R sub F times this input voltage, which is V2 minus V1, and that should give us V1 minus V2. So this is our final answer. And this is our circuit. So we used three op-amps to accomplish this function. Now there's a possibility that we could only use two op-amps, and uh, I will leave that up to you to check if that is possible.